Hello, I'm Theresa, Associate Professor at Montana Tech, and this learning unit will introduce calibration, measurement, and error. In this learning unit, we'll cover some measurement considerations, start to discuss the different types of error and how to control them. Calibration standards, I'll introduce pumps and sampling as well as calibration trains. Calibration and primary standards. So what is calibration? Well, calibration is setting or correcting of a measuring device, and for us we'll be using a sampling pump of some type, by adjusting it to match or conform to a dependably known, unvarying standard. So that's what calibration is. So what exactly is our sampling pump doing when it's sampling? So most integrated monitors for airborne particles, aerosols, gases, and vapors require some type of battery-operated air sampling pump. And we know that this is active sampling. So the sampling pump draws air over the media in through the pump. The sampling air is pulling air at a volume over time. So this is considered our flow rate. So our basic calculation or our basic formula that we'll be using is Q, which is your volume over time, usually expressed in liters per minute. So for example, we'll be setting our sampling pump to 2 liters per minute. Now it's important to calibrate both pre and post sampling campaign because the flexible hose and the sampling media, as well as any debris that builds up on our sampling media, creates friction or drag, and that needs to be accounted for when we set our appropriate flow rate. And our flow rate is very important to ensure that the results that we got are considered valid. And we'll learn later on in this course when we go through analytical methods how to find the appropriate flow rate. So we calibrate our sampling pump to reduce errors. We check if the instrument is within our qualitative parameters. We must remember that battery-operated instruments are particularly susceptible to fluctuations due to voltage loss, and our sampling pumps do try to adjust for any fluctuations within a certain range. Also, mechanical operating instruments such as our sampling pumps can have parts that become worn out, filters or inlets or outlets which become clogged over time. So we calibrate to a primary standard, and here are some examples of primary standards. We have a piston calibrator or a dry cal. We have a calibrator that is also called a bubble calibrator. Then we have electrical devices such as our sound level meters. And then we have calibration gases. So these are different types of primary standards. We calibrate to a primary standard to set the rate at which the pump will pull air at, as well as to verify that rate. And you can check the link out for the OSHA technical manual, and it describes proper calibration techniques, which we will use here in this class. So bubble barrettes are also now considered secondary standards, although some people still use them as primary standards. So for measured concentrations, we have our calibration gas or our noise emitters. Our primary standards are within 1% of error rate. This is what the OSHA technical manual recommends, and that is one of the reasons why they recommend the use of a volumetric displacement device, which is our dry cal. This is within 0.5% of accuracy. OSHA considers this a primary standard, and it'll measure how much air is being pulled through our sampling device. So the first type of primary standard is an electronic dry piston flow meter. And I'm going to show you an example of that. Okay, so I have my sampling pump here. It's been running for 5 minutes and it's warmed up. Connected to the inlet, I have my sampling media. This is exactly like the sampling media that I'm going to sample with, although I've labeled it as a calibration media, so I'm only going to use it for calibration. Connected to the inlet, I have another tube, and now I'm connected to my primary standard. You can see the pump, the volumetric displacement. There's a cylinder in there and a metal piston that's going up and down at a certain rate. The volume of that cylinder cannot change, and it's measuring how much air, how fast the air is being pulled through the pump. So you can see that my average flow rate is about 2 liters per minute. Oops. Volumetric displacement. This is my calibration train. If I unhooked my calibrator, this is my sampling train with representative media inline. Another type of primary standard is electronic bubble meter. And so a bubble of soap solution flows up a set volume, and using an infrared sensor, you're able to measure the flow rate based on when the bubble passes one sensor and when the bubble passes another sensor. So this is the same type of primary standard, but instead of using volumetric displacement, it uses infrared sensors to measure how fast that bubble is traveling within a tube. The common name for these is a calibrator. There's also other bubble meters. Other types of primary standards, if we have a gas detector, such as a photoionization gas detector, we would use a known calibration gas that would come in a bottle for us, as well as noise meters. You calibrate against a known sound pressure level. Also in ergonomics, we have primary standards that we use for calibrating vibration exposure as well as acceleration, so an accelerometer. So when do we calibrate? We calibrate before we sample to check or set the flow rate to make sure we're pulling air at the appropriate volume per minute. And then after we sample, we don't touch our pump, but we check the flow rate to see if there's a significant difference or not. So how do we calibrate? We calibrate after our pump has been warmed up. We calibrate with a representative sampling media inline. That's exactly as we're going to sample. We calibrate the pump every time, before every time we sample, and we try to do our pre and our post calibrations there and about at the same sampling conditions. And here is just another example of a sampling train, not a calibration train. You have your pump connected to your inlet. Here's your Tygon tubing, and it's connected to your inlet of your cyclone. Actually, the air is pulled in here hands gently to the cyclone, it spins around, and the media, the particles that are too heavy fall down in the grit pot. Those that are light enough attach themselves to our filter. So we calibrate before we sample, pre-calibration, to set the appropriate flow rate. And this is also a check to see if our pump is performing appropriately. After we're done sampling, then we post-calibrate our pump as soon after the sampling campaign ends as possible. We don't make any adjustments to our pump. We just check the flow rate to see if it's within a certain range or not. If it differs by too much, we might not be able to use our data. Also, we need to calculate a sample volume. We have to send a sample volume to the lab, which is going to be based on what our flow rate was and the time for which we sampled. And we will do some calculations together. So how do we determine what our percent error is? Well, we use this calculation right here. Our flow rate before we sampled, our flow rate after we sampled, divided by the flow rate before we sampled, and this will give us our percent error. If the pre and post flow rate is 5% or less, then we use the average when we calculate our sample volume to report that to the lab. If our flow rate error was between 5 and 10%, then we need to use whichever one was lower, either the pre-cal or the post-cal. If our percent error is greater than 10%, then we should really consider resampling. Some people will again use the lower flow rate, either the pre or the post, but the AIHA guidance document tells us that we should really consider resampling. So just to state that again, we calibrate before we sample, then we sample. We calibrate after we sample, and we have these two flow rates. They're going to differ. If they differ by less than 10%, we take the average, which is flow rate before plus flow rate after, divided by 2, and we use this to calculate our sample volume. If they differ by between 5 and 10%, then we use the lower of the two flow rates. If they differ by greater than 10%, then we should consider resampling. And we'll now do a calculation. When I pre-calibrated my pump before I sampled, I was able to set it at 2 liters per minute. My post-calibration is 2.08 liters per minute, and I sampled for 5 hours. So our first formula is flow, Q, equals V over T. Our next formula for our percent error, Q pre minus Q post over Q pre. So let's run this equation. What's our percent error? Would be 2 minus 2.08 divided by 2. I have a 4% error. Because I have a 4% error, I can use the average flow rate to now calculate my sample volume. So my Q average is pre plus post divided by 2, and it's divided by 2 because there's not two variables. Don't be confused with this 2. So I have 2 plus 2.08 divided by 2. My average flow rate for 5 hours was 2.04 liters per minute. Now I need to use this to come up with a sample volume to send to the lab. I'm just going to use this formula right here. Q equals V over T. So that's 2.04 equals some volume over my time. So I had 5 hours times 60 minutes in an hour would give me 300 minutes. This was liters per minute. I'm going to multiply by isolating my variable. 2.04 times 300 means that I have 612 liters of air over my 5 hours, and this now is the sample volume that I'll use and send to the lab. Okay, let's do one more practice problem together. We pre and post calibrated our pump and we came up with an average flow of 3 liters per minute. We sampled for 480 minutes, and the mass found, the concentration that came back from the lab was 7 milligrams. So what is the concentration in milligrams per meters cubed? Well, we need this conversion factor here. So let's first start with our sample volume, finding what our sample volume was. And we need this because our concentration is mass over volume, right? So our flow is volume over time, but our concentration is mass over volume. So first let's find our volume. We have 3 liters per minute. It equals some volume over 480 minutes. When I bring this over here and multiply, my minutes will cancel out. I have 1,440 liters. But I need to convert that into meters cubed. So I'm going to multiply it by 0.001. And now I have 1.44 meters cubed. That's my volume. My mass was 7 milligrams. So what was my concentration, the exposure for which I feel my workers were exposed to? Well, I take my 7 milligrams and I divide it by 1.44 meters cubed, and I come up with 4.86 milligrams per meters cubed. Okay, parts of a sampling pump. Pretty difficult because they are different, but in a way, many of them are the same. So these are the sampling pumps we have here at Montana Tech. You will become familiar with them when you come visit. They have an on-off switch They have a tiny set screw here that you turn to be able to move the flow higher or lower. You have a digital timer there that'll count how long the pump has been running. You have a built-in rotometer, which is a way that you can visually see what the pump is running at. And although you cannot use it for calibration purposes, you can get an idea of whether the pump is running within the appropriate range while you're sampling, so you can use it as an observational check. These pumps come with low flow adapters, so you can turn the flow down so you can get down to 0.1 liters per minute. And of course, they have some form of charging station so that you can charge them or plug them in different parts of your sampling pump. So this is another example of a calibration train. This is your pump. This is your media, which is inline, and this is your primary standard. So the flow rate is going in this direction because it's going across the inlet. You want it to go across the inlet because that's where the material is going to be deposited, towards the pump. Again, which way is the air flowing? It's flowing towards the pump across your filter cassette. So we always sample with what a representative media in line. It means typically what's done is you get a box of cassettes and you pull out the 1 or 2 that you're going to use for calibration purposes. Then you pull out the 4 or 10 that you're going to use for blanks, and the rest of the media left in that box is your sampling media. Your calibration media blank should come from the same set, the same lot number as your sampling media. Some people will reuse their calibration media over and over again, and at some point that may actually introduce error. It could get dirty, or there can be some anomaly in the way the sampling media was made from lot to lot. And remember that we are calibrating with our representative sampling media inline because it introduces some kind of drag in your system, and you want to calibrate exactly like you're going to sample. So your calibration train is your calibrator, your media, all the hosing, and your sampling pump, whereas your sampling train is just your pump, your flexible hosing, and your sampling media. So while you're sampling, you can use your built-in rotometer to see where the pump is running. We can use this as a reference point. You can feel the pump to make sure it's still running. Talk to your workers, of course. If it became fouled, they can tell you. Again, we need to do our pre and post calibration. If the difference between the pre and the post is greater than 10%, it's considered unacceptable. You throw it out or use the lowest flow. If it's between 5 and 10, AIHA says use the lowest flow. If it's less than 5, then we can use the average. So we're going to talk a little bit more about our measurement considerations in our error, because ultimately what we're trying to do is come as close to the truth as we possibly can, but of course we don't know what the truth is. So there are 2 terms that are used interchangeably. One is precision or reliability, and that is our random error. And then we have our validity or accuracy, and that's our systematic error. Precision could be seen as, are we measuring what we think we're measuring? Are we trying to sample for benzene when we really have hydrogen sulfide in the air? Well, then we're not being very precise. And validity or accuracy is, are we getting the same results in the same conditions every time we sample? Are we being repeatably accurate so that our samples can be accurate? And we'll go through another piece of material on that in just one moment. So here's my sampling pump, and you can see right over here is my rotometer, and where that bubble is after I set my sampling flow rate, I can look where the bubble is on the rotometer, and if that is there in about the same place every time I come back and check my sampling media, then I can be fairly certain that my flow rate hasn't changed. Now, of course, I'll go back and I'll post-calibrate, but that's what you can use your rotometer for. You can see it's kind of a visual indication of where your flow is. And now I'm just going to turn it down so you can see the rotometer change. You can also hear the pump change its speed like on a car, and if it becomes fouled, then it would shut itself off so it doesn't explode. But sometimes your workers can hear that if a hose becomes pinched and unpinch it for you. So we're going to talk a little bit more about precision and validity. Precision is when we have nearly the same measurement each time that we sample, if we're sampling in the same environment and we're sampling the same way. A way to think about that would be if you got on your scale every hour and it weighed 130 pounds, that measurement would be precise. It'd weigh you the same every time. But a precise measurement may not be accurate. If my scale was 5 pounds off and it measured me at 130, even though it was precise, it measured 130 over and over and over again, because it was 5 pounds off, it wasn't actually accurate. So accuracy, are we measuring what we should? And precision, are our measurements repeatable? Precision is random error, and accuracy is systematic error. And I'm going to play a video now that can describe this.
Accuracy and validity are related. Precision and reliability are related. Accurate data is truthful. It tells us what nature is really like. And if it's accurate, it's also valid. Precise data is repeatable. It's predictable. We get the same answer again and again when we repeat ourselves. To understand this better, let's take a look at this analogy. Let's say that each of these little crosses is a measurement about something. In the background, you can see a target. We have the bull's eye in the middle. The bull's eye, the center of the target, is representing the truth about the thing we were measuring. So let's say we were trying to measure what is the mass of 10 milliliters of water. Let's say that that answer, the answer is 10 grams, is represented by the bullseye. So if we take a measurement and we get our answer 10 grams, we're right. We're being accurate. Our readings are truthful. They are valid. So maybe 4 times we take the same measurement. What is the mass of 10 milliliters of water? And we get very slightly different answers, but all close to the truth of 10 grams. So we get 9,9 and 9,8 and 10 and 10,1. We're varying a little bit in our data, but not very much, and it's all around about the correct answer. Then we call our data set here accurate, so it is valid. In comparison, you can see data C and data B are not accurate. We're busy measuring something quite different from the real value. Instead of measuring 10 grams, we may be measuring 8 grams or 7 grams, which is not the truth. B and C's data readings are not accurate. They are inaccurate. They are not valid. They are invalid. What about precision and reliability? If data is precise, then if you measure the same reading again and again, you get a very similar reading each time. So you can predict what your next measurement will be by looking at what you've just measured. If you measure precisely, then you will also see a trend in the data easily. You'll see a pattern. Whereas if you're being imprecise, you won't be able to predict what the next reading will be as you vary the independent variable, because your readings are all over the place and erratic, and so you can't trust them at all. You can't predict based on any pattern because you can't see the pattern because you're reading all over the place. So we can see that data A and data B are both precise because the readings that we take of the same thing are similar to one another. That reading and that reading are quite similar. That one's also similar, and that one as well. And the same here. All those readings are similar to one another. We're being precise. B is precise even though it's inaccurate. It's reliable even though it's not valid. B is inaccurate, invalid, but precise and reliable. A is accurate, therefore valid, and precise and reliable. But if we look at C, well, the readings are all over the place. So maybe we're measuring the mass of 10 milliliters of water. One reading we find the mass to be 8 grams, and then it's 7 grams. The next reading it's 6 grams. We're reading all sorts of different values for the same thing. We are not being precise. This is imprecise, and so it's unreliable. It's also inaccurate, not valid, because...
So we're trying to ensure that we, minimize our errors. And we want to minimize our errors due to precision or errors due to inaccuracy or imprecise. So when we choose our sampling method, we have to ensure that it will measure at the level that we want it to, the agent of concern, and that there isn't anything that'll conflict with our measuring of whatever it is that we're measuring. So the easiest example of this would be if you have a lot of pet dander in a room, and yet you're trying to measure for asbestos and you're using the granular counting method, somebody may assume that all the fibers that they see are asbestos fibers when really they're dog or cat hair dander fibers. And these can actually be easily confused with one another. So we may choose a different method based on the confounding variable of having too much dog hair in our environment. And for precision, precision would be ensuring that we calibrate, pre and post calibrate our pump, that we handle our media in the right method that is appropriate for it when we before we sample, during sampling, and when we pack it up and ship it out. We can definitely influence our precision and our accuracy. And we'll talk a little bit more about the limit of quantification and the limit of detection later on in the course. So we're trying to seek the truth through repetition. We do our data analysis to ensure that our quality is being controlled. We have a sound sampling plan and strategy with objectives in place before we enter our work environment, before we choose to sample. And we are certain, or we try as much as possible to reduce errors that we may introduce. So random fluctuations in the flow rate, we can do this through checking our pre and post calibration, and then also in our observational methods of taking a visual of that rotometer over time. Ensure that we have the correct laboratory analysis for the agent that we're sampling, that we don't have any observer or subject bias, so that's who we sample. Are we sampling the people that are most compliant? Are we sampling the people that have been there the longest? Or did we actually randomly choose the people in the shifts that we're going to sample? Are we taking enough samples, one continuous sample or integrated sampling throughout the day? Did we put people in appropriate similar exposure groups? And are there day-to-day fluctuations? Maybe production is higher on a Wednesday and lower on a Friday, or higher on night shift and lower during day shift. So we have to look for these interday or interweek fluctuations. So other sources of error would be not knowing enough about the job or IDing the chemicals that are in the workplace or any additive toxic properties. Incorrectly using the worst case scenario for your initial evaluation and then assuming that everybody is exposed at that rate, or not documenting your times or where your workers were within the process, and when you get your results back, you can't extrapolate or generalize them. Also, did you miss something in your exposure pattern because you took one continuous sample instead of integrated samples over a period of time? Did you sample for too long or too short of a period, which is more likely? Did you miss your short-term samplings for your STELs? So this is how we try as much as possible to avoid our bias or our errors. In our next lecture, we're going to look at our standard analytical errors, which are errors that are introduced from the laboratory themselves. The laboratory isn't exactly always accurate, and we can use these standard analytical errors to put confidence intervals on our time-weighted average, and then use that as a comparison to be certain if somebody's within or outside of compliance. And we'll look at our standard analytical errors a little bit later. But first I'm going to do two more example problems for you. And this serves as our introduction to calibrating, sampling pumps, and different types of errors that we're going to try to guard against when we're sampling. So another example calculation. We pre-calibrated at 2.5 liters per minute. We post-calibrated at 2.9 liters per minute. So what's the sample volume that we report to the lab and why? So first, what's our percent error? So we have our 2.5 minus 2.9 over 2.5. So we have a 16% error. With a 16% error, we cannot use the average. AIHA recommends that we throw the data out. If we'd like to use it, then we need to use the lowest of the two flow rates. So we can use 2.5 liters per minute here if you choose to. So we can have our Q equals V over T. Our 2.5 liters per minute equals some sample volume over 480 minutes, and these will cancel out when I isolate my variable. So my sample volume was 1,200 liters.